We already know that any combinational circuit can be made using decoders and OR gates. In this particular question, we will illustrate how to implement full adder circuit using a decoder and two OR gates. We're going to start with particular steps which are the same for every single question from this type. So the first one, we will have to figure out the number of inputs and number of outputs. Considering that we are implementing full adder, we already know that there are 3 inputs and 2 outputs. If we call the inputs x, y, and z, the outputs are always the same, S standing for sum and C that stands for carry. So the result in here, what we will put actually for the first step, is the following. The next step will be to figure out the number of minterms, and we're using the formula which is 2 to the power of n. N is the number of inputs. Because we have 3 inputs in here, 2 to n is going to be 2 to 3, so we are going to have 8 number of minterms. Next step is related directly to organizing our diagram, so it's going to be creating a minterm table. The actual minterm table is going to consider number of inputs, number of outputs, and every single row with respect to will be related to a respective minterm. So let's go ahead and start creating our minterm table. As we can see, in the input columns, we have already organized x, y, and z, and the outputs are S for sum and C for carry. Every single row is related to a particular minterm. We start notating them from M0, so the first one will be M0, the very last is going to be M7. Next, we're going to do the calculations for the sum and for carry. Doing the sum means that we have to literally add the values for x, y, and z, keeping in mind that we are doing Boolean algebra in here. So 0 plus 0 plus 0 is going to give us the summation of 0, and the carry is going to be 0. M1 will end up on sum being 1, carry 0. We're going to have exactly the same for M2. M3 will require a little work. When we do the calculation for M3, we're going to have 1 added to 1, which is going to give us summation of 0, and the carry is going to be 1. M4 remains 1, 0. M5 is exactly the same as M3, so it's going to be 0, 1. Same applies for M6. Now for M7, we're going to use the calculation before. We have 1 plus 1, and to the result we have to add 1. So I will use my older calculation in here. 1 plus 1 gave me sum of 0 and carry of 1. Now if I add 1 in here, I will end up on a sum of 1 and carry of 1. Which means for M7, we can put 1, 1. Next, I will organize all the values of 1 which belong to the sum, and I will use a red color in here. Then I will do exactly the same for the carry, but this time I will use blue. Now I'm ready to write the summation expression for all the minterms, respectively for S and C. And here is the answer. Next is to move ahead with the logic circuit. We will use a rectangular symbol for the decoder. One small note in here, because we're having 3 inputs and 8 minterms, this means that the type of decoder we're going to use is going to be 3 to 8. Next, we'll organize all the outputs from the pins for the minterms, which are going to be combined together as inputs for an OR gate, That will give us the output S. So let's do that. We are using minterm 1, minterm 2, minterm 4, and minterm 7. The ones which are going to be connected to the gate providing output of C are going to be respectively 3, minterm 3, minterm 5, 6, and again 7. From here ahead, we're going to just draw the respective gates. So here is the decoder. We're going to attach in here the outputs which are coming from each minterm, and we will keep the same color code. The red ones are going to be the one related to the sum, and the blue ones are going to be the ones related to the carry. If you notice, the minterm 7 has actually a red line and a blue line because it's a minterm which is shared between the inputs for the sum and the inputs for the carry. The next step is just to attach the respective OR gates, and we will be done.